Thank you very much. This is a joint presentation with José Antonio Langa and José Ramón Portillo. We come from the Universidad de Sevilla in Spain, and well, they are mathematicians and I'm a philosopher and computer scientist. In this work, I'm more a computer scientist. Well, we are working with systems of this kind, systems of interacting elements with a behavior regulated by equations in this way. This is a dynamical system, a well-known dynamical system in ecology, which is Losca-Volterra, in which there are interactions that affect only one node, positive when the interaction is activating, or negative when the interaction is deactivating, and interactions between different nodes that contribute to increase or decrease the activity of the nodes. Well, once we set a system by giving a set of parameters, that system has a set of stationary points, which are spatial points in which the dynamics of the system remains the same, doesn't change. Not all the stationary points, those are the stationary point, that is values of the variables, values of A, B, and C, that make that the system doesn't change. And we can represent in a graph what we call the information structure, that is the structure of the global attractor of the dynamical system. It is a mathematical, abstract mathematical structure that contains all stationary points, or a representation of the stationary point of the system, and the links representing solutions to the future and to the past of the dynamics of the system. Well, this is a natural abstract mathematical structure, and we can extend, or we call it an information structure because it provides information to every point in the phase space of the system. Sorry for my this is a simple information structure with 4 nodes. If we represent the nodes with the real values in the plane, we get a vector space giving the direction of change of every point in the phase space of the system, and by providing what in mathematics they call a Lyapunov function, we get an energy landscape that we call information field, because it provides information to every point. It gives the directions to the future and to the past to every point in the space of the system. So this is the theoretical basis of our approach. To brief the systems with a dynamics, it produces an information structure that is what is behind the system, behind the dynamics of the system, and the information structure provides information to every point in the phase space of the system. Well, in previous works we have applied this approach to consciousness mostly in the framework of integrated information theory, and what mostly I'm going to present today is the results of a very recent paper, well, a paper published today. The uncorrected proof, so it's online today. And when we apply this formalism to the classification of different brain states or state of consciousness in healthy controls and also patients with minimally conscious state or unresponsive weakening state. The paper is with other people that we thank by their contribution, people from Liege, Steven Laures and collaborator, and people from Paris, like Jacobo Sid, also Gustavo Deco, Morten Kinkerbach. It's a big thing. What have we done? Well, we have data from people, healthy control, but also patients from Liege and Paris. We have two different data sets of data obtained by neuroimage, fMRI, and the brain activity is mapped in the 7 area, the 7 brain networks of the geoparcellation. It is a very simple parcellation, a functional parcellation with 7 brain networks. And there is a mathematical procedure to get from the data of the system, the data produced by the system, in this case the time series corresponding to the activity in the 7 brain networks. There is a procedure that is a Lotka-Volterra transform, a model transform, to get the parameters of the system, the parameter of this system of interacting elements. We need also to get those parameters. We need a connectivity matrix. We use structural connectivity matrices in the transformation, and we get the parameters of the system, of the parameters of a Lotka-Volterra system, and then we can build the attractor landscape in each instant. At each time point, we have an information structure of a very simple system, only 7 nodes, but it can have up to the power of 7, 128 nodes. So we get for each participant at each time point an information structure. And we apply several measures to those structures. I will show the measures that we apply. This is an example of an information structure. It is exactly the same as the previous information structures, but instead of having A, B, and C, we have brain networks. Brain networks, those are the stationary points, and brain networks in color represent stationary point in which that brain network has a value greater than 0. And, there is a structure because there are those connections that I told you that are the solutions to the future and the past in the dynamical system. And we can look at the structure of the attractor and measure it in several ways. For example, we can look at the number of energy levels. Noel is number of energy levels. These have 1, 2, 3, 4, 5 layers, which are levels of energy, also called. We can look at a measure that we call frondosity, which is the amount of nodes in the structure divided by the maximum possible numbers of the node with that energy levels. For example, in a structure with 4 energy levels, we may have up to 16 nodes, but this structure has only 10 nodes. So 10 divided by 16 is the frondosity of that structure. And there are other measures that we call cooperation measures that look at the interaction between networks, not in the dynamical system, but in the information structure that is behind it. For example, we see that only somatomotor and the default network are in level 1. Those are networks that may exist in the information structure by themselves. They can exist alone. But there are other networks like visual attention, frontoparietal, that don't appear alone, but can appear in presence of another one. So we can this a cooperative node, and we can measure the number of cooperative nodes that appear in the information structure, and we can count those nodes in several different ways. We have 3 cooperative nodes, and depending on the way that we count them, we have different measures. Well, and we have the result of this work is that we find differences in the measures of information structure that depend on the level of consciousness of the participants. For example, a very simple measure, that is the number of energy levels, we find that unconscious patients have structures with a greater number of energy levels. Why? Because those structures are more trivial. All the networks appear at every time. And there is also lower variability. The standard deviation, the mean, is high, and the standard deviation is low. There is less variability. And we say that the standard deviation of the number of energy levels is a measure of metastability, because it is the tendency of the system to change the attractors. And we say that we see that the activity in unconscious patients is more trivial than in healthy controls. Similarly with frondosity, the variability of frondosity denotes a richer information structure landscape, because there are more differences between or among the information structures. In the case of unresponsive subjects, all frondosity equal to 1 means that all possible nodes are in the structure, and it is produced when the activity is almost trivial, because there are not cooperative interactions, and the structure is always the same. With respect to, well, criticality is another interesting measure. I didn't talk about it because it cannot be measured in the structure of the attractor by looking at the specific parameters of the system. Criticality measures how close are the parameters of the system to a bifurcation, and we call a bifurcation a point in which the shape of the structure, of the information structure, changes, and the global stable solution is changed, is a different solution. Lower criticality means that the system is behaving closer to those grid changes in the attractor, because criticality is proximity to a bifurcation. So lower criticality is closer to the bifurcation, and it is interesting the result with the criticality, and it agrees with the idea that consciousness is released by brain configuration that are between order and chaos. Well, synchronicity is measures the ratio of information structures in which all brain networks are in the same state in the global stable solution. that is, all brain networks are present or absent of the global stable solution. A higher synchronicity means that all networks are behaving in the same way. And finally, cooperation. Well, cooperation measures the interaction, the strong interactions between brain networks and able to activate one network because of the activity and the cooperation of another one network or a set of other networks. And we see that healthy control have higher levels of cooperation than patients with impaired consciousness. And well, an interesting result that we have got with cooperation is that we look in a closer way to the frequency in which each network appears in the global stable point of the information structure. How frequently a particular network appears in the global stable solution. And in all cases, this is the average of all healthy controls, the average of all patients in minimally conscious state, and the average of all patients in unresponsive wakening state. The value is very high in any case because the values go from 0.8 to 1, so the value is very high. But if we look not at all the occurrences of the brain networks in the global stationary point, but the occurrences due to cooperation, that is, occurrences of a network in the stationary point that is a product of the cooperation of other networks, we get a very different picture. We find very much cooperation in cooperative interactions, in healthy controls, and much lower values in patients with impaired consciousness, minimally and unresponsive. An interesting result is that the brain network with higher values of cooperation are the formal networks and frontoparietal, and it agrees with several studies of the relevance of those networks in consciousness. And well, finally, well, not finally, we have applied machine learning to classify the conscious state of the patients by looking at the measures on informational structures, and we have got very good classification with machine learning, and well, very good, but in line with other approaches and with other papers in the literature. Our interest in machine learning is not so much the classification of particular subjects, but to look at what measures are the most important to detect differences in consciousness. And well, in conclusion, well, I think that an important point of our work is that we are using dynamical system, we are using the differential equation, Log-Terra system, that is attractor, but in a very different way of the usual approaches of dynamical system in whole brain models, for example, where the use of the dynamical system is to look at the change of the system. The system is changing too much, or the system is changing in a very complex way, so it needs consciousness. Well, we are not looking at the changes in the system, but at the structures that are behind the system at each particular step. So we are interested, and we think that it is more in line with the theories of consciousness, for example, with integrated information theory, that we don't look at what is the system producing, but how is the system at this particular moment, and how is the structure representing the information in the system that is behind it. And also the kind of approach that we have applied to consciousness provides a richer understanding of certain notions commonly related with consciousness. We have a sound mathematical framework because it is a dynamical system, very well known in mathematics, with theorems proving the properties of those systems. And for example, criticality, which is a property commonly related with consciousness, but we don't know which is criticality. We can define it by looking at the parameter and by measuring how close are the parameter to a bifurcation point. And well, there are very much interesting things about criticality that we are now developing because we are applying those systems to neuroscience and also to ecology, and this is a very important measure. Another example is metastability. That is another measure or another property commonly related to consciousness, and the kind of system that we are using are a natural source of metastability, an informational structure in an informational structure, or stationary points that are not stable are metastable because they have directions of stability and directions of instability. And they are producing metastability in a natural way, in a way that we can handle mathematically. And not only the intuition is good, but if you have mathematical tools, it is better. And integration and differentiation, which are very, very, very important properties of consciousness, or commonly related to consciousness, can be related also with measures like synchronicity, cooperation, and other things that we can look at the structure of the attractor, at the informational structure. Also, it is nice that in the attractor we have the measures that we apply to it, but we also have a particular chain, so it allows to see also differences, like the differences that are in conscious experience between, for example, the quantitative and the qualitative. We have numeric measures, but we also have a structure with a chain. And that's all. Thank you very much.